is different. So I can suggest that you can read a proof from Huffman and Kunz. Okay, but because of our short time, let me just give you a proof. Let's see. This is some density argument. So Cayley Hamilton theorem. Let's try to prove it. So let's take an arbitrary field and let's look at this ring. Okay, and let's say that the other way, but okay, I'm just writing it like this. Okay. So there is this thing, and then you have defined the characteristic polynomial of A. This is already defined. Determinant of A minus lambda I. And then the theorem claims that this thing is equal to 0. Okay. Obviously, this is a zero matrix. So why is it? Yeah. So let us see in one case where it is obviously true. Okay. If this has n distinct roots, if this has n distinct roots, not a problem. Okay. If this has n distinct roots, then you can write, let's say the roots are lambda 1, lambda 2, and so on, right? Then you can factorize it like, it's a monic polynomial. That is fine, right? Is this okay? This is the way of bringing in your polynomial knowledge of polynomials. If this polynomial has n distinct roots, then what happens?
Okay.
Okay. So this is a sort of an important thing. Now, what do you want to show? Now we need to show that this thing, you see, now here the one will become identity because now this is being evaluated as matrices, as a polynomial with the variable replaced by a matrix. Okay. So this is we need to be careful. Right. We need to show that this is equal to 0.
This is equal to 0 if
Matrix. If this is true, yeah.
Okay.
Under this condition, we need to show that this is 0. Right. Right. Correct. So, in fact, you don't need to assume this something that will work, but this is we need to show this is 0. So now imagine that if again further another assumption is if A was a matrix like this, diagonal matrix, then you can see that this is true, right? If A is a diagonal matrix, then the LHS just above, what does it become equal to? It becomes equal to 0, lambda 2 minus lambda 1, lambda 3 minus lambda 1, and so on, right?
yes.
Times this will become
Lambda 1 minus lambda 2.
right, 0, and then so on, right? And like this. And when you multiply diagonal matrices, you just multiply column the components, and this will become 0, 0, 0.
0.
Right. So for this kind of matrix and with this kind of condition, it is. Okay. Now we need to show, now here is a claim, and I don't think I can prove that, right? I don't think we can prove that. It needs another concept called base. So I will just assume this. If there is a matrix P such that PA P inverse is diagonal, then you are done. So let's call this A prime. Okay. Now A prime is like that. And if this happens, then you are done. Why?
And
Because yes, because if this happens, if starting with your A, which has this nice characteristic polynomial, and if you can conjugate it and make it into a diagonal matrix like this, it will be like this. But if it assume that, then you are done, because then this A, because okay, then you can see first of all that this is true. This is just what we already said. Maybe
yes, this is
right, yeah. So you know that this is true, right? And now you multiply by P inverse on both sides. One on
where
left
the
side
P
by
belongs,
sorry,
the P belongs to.
it can only belong to MNF, right? No other place it can belong. Otherwise, you can't multiply it. P belongs to MNF. Okay.
Okay.
Right. There's no other way. Check the dimensions. Right. And then you just what you do is you multiply by P on this side and multiply by P inverse on this side or something like that. Right. In between, you do P inverse P, some kind of juggling like that, and you can do. Right. Then because then you will get A, right? Because A is also P inverse A prime. Maybe P inverse you do. So like this, you have to do P inverse P, which may put, which doesn't affect because it's identity. And left and right also you attack by P and P inverse. Right? Then basically this thing will become, and this is a very nice thing that happens, lambda, and this I will remain I because the P inverse will get cancelled, right? And similarly you have,
We don't know these matrices are commutative or not.
no, that's why it's not commutative. That's why I'm writing this like this. But P and P inverse are commutative with each other.
Yes,
Yeah,
they are commutative.
that's all. That's all you need to know, right? And these are cancelling, right?
Hmm.
Basically, from here you can get the same thing for A if this happens. Okay, so that is the thing. Yeah. And then there is a density argument, which I can tell you. What the density argument says is, just to tell you here in short, because I think you would not be very comfortable with that, but just tell you right now, and then there is this argument that given any B in M and F, okay, given any B in M and F, okay, I'll first say like, so if you assume that F is equal to R for now, okay, then given any B in M and F, there exists a sequence of matrices that now that you know convergence in Rn and so on, which converge to B, such that these things have this property star one, this property star one. Okay, and this property star two, which I have written, is actually implied by star one. Okay, or yeah, that's it. Right? So these have property star one. That's a fact. Given any matrix, there is a sequence of matrices that converge to it, which have this property. So then what happens is, then basically this thing is equal to 0 because we have proof for this kind of matrices. And then you can take limit. And this characteristic polynomial is a continuous function. The coefficients are continuous, and so you can take the limit inside, and this will be complete. Okay, so that is one of the things. The other thing is actually more abstract if you want to go for arbitrary fields. So I'll leave it, not say it. For arbitrary fields, you have to introduce what is called the Zariski topology. And so, yeah, and if you can show that this is continuous with respect to that, and then this is true on a dense set, then it will be true everywhere because it's continuous, right? So, but I cannot explain that because that I need the language of topology. That's a very nice thing, but yeah, that proves it. Otherwise, if you look at Hoffman and Kunz, there is some several pages proofs, some calculations, they keep calculating and then they give. This is more conceptual. So you see, basically the idea here is that it is true for nice matrices, and then you show that those nice matrices are everywhere. Okay, and so it's true for everything because this thing that is being true is a continuous thing. So it's true in a dense set, then it's true everywhere. So this is a mixture of things. But I hope all this will come in. These things are called eigenvalues, eigenvectors, and something called Jordan canonical form, which is one of the milestones in linear algebra, which you should reach. Then it's more easier to talk. Okay. Anyways, let's stop here, and then we'll meet on Sunday. You can read this. I think Hoffman and Kunz, you'll find this, and just work out some examples. That's actually more important, very important. Work out the examples.
Examples of
Cayley Hamilton,
what?
some simple examples of Cayley Hamilton, right? Small matrices they will give, and they will look at the section in Hoffman and Kunz. Even Wikipedia has a nice article on Cayley Hamilton. You can see, I give some history and so on. Artin will also have to see the index and just see the whatever index of content. Okay. All right, and this is
the Nakayama algebra.
No, it's a Nakayama lemma, right? So the Nakayama lemma is a generalization of this. I can tell you, I like these kind of things. So what the Nakayama lemma? So what? First of all, if you try to view what you have learned right now, then you will see that what you have learned is that given a vector space V to V, and given a transformation T, given a vector space V and given a transformation T, I will show you why this is what we have learned. But first, let me tell you this. You have this, and then basically there is a polynomial in this transformation which gives you the zero transformation. Because see, when you have a transformation from V to V, then you have T square is also a transformation, is composed again, right? And adding two is also, so basically you can form a polynomial. Okay, so you can take a transformation like T square plus T is also a transformation, but this is understood what this is doing. It is taking V to T.
P of T, that means?
P of T means polynomial evaluated at T.
Okay.
Yeah, so yeah, this will be like x square plus x of T. This.
Yeah.
Okay. Yeah, and then the Nakayama lemma, and so what you have proved, Cayley Hamilton has proved that such a polynomial exists, and the degree of that polynomial is not more than n. Right? Because this transformation is that matrix. Because for every transformation you have a matrix, and that matrix becomes 0, then the transformation becomes 0, so on and so on. But what Nakayama lemma does, it generalizes this very nicely, and the proof remains almost the same. Or obviously, then you have to give an algebraic proof. I think then you cannot give these arguments like R and so on, because then you're no longer over a field. Okay. So what it does is it says that you replace this vector space by an abelian group. Okay. And it's a module, so it becomes a vector space over a ring, and so it's no longer over a field. It's a ring, and then you have so basically it's just a vector space, but the field is replaced by a ring, so it becomes much more abstract. Okay. And then this module is finitely generated because now we don't have concept of basis every time. obviously all life spent in figuring out which modules are basis, but that's a lifelong thing, I think, to do. Yeah, and do research on that. But in general, they don't have. But then they still say that if you have T, which is a map, which is a linear map, it's called an endomorphism here, but the same thing, transformation. Okay. Then again, the same thing is some things more are true, and it's actually a very fundamental result. But this is the Nakayama lemma is this setting. And when you prove in this setting, then this is also done. Because if you just replace R by B, R by F, and this was the thing. But prove the general thing, I don't think it's good to do now. Okay. Yeah, and if you want to read this is chapter 2 in Atiyah McDonald commutative algebra. Chapter 2, but right now.
Chapter 2 of?
So there's a book, Commutative Algebra by Atiyah McDonald. Atiyah and McDonald. Atiyah, you know, right? Michael Atiyah, very famous theoretical physicist and geometer. I think you're yeah. And McDonald, I don't know if it's the same McDonald, but he's, I don't know which McDonald.
The book name is
Commutative Algebra, but it's a tough read. I mean, it's better to, yeah, commutative algebra. Right now, it's above 13, and it's beyond. It's much harder than. Yeah. They focus on rings in general. Book, nice book. Okay, all right. I'll stop here. Okay.
Okay, then send it to